Welcome, everyone. I am absolutely thrilled you're here. Today, we're diving into a fascinating explainer on what is essentially a planetary scale machine. We're going to break down Earth's hydrology. The incredible, dynamic systems that move water from the upper atmosphere across our relentless surface rivers and deep into the invisible, highly pressurized world underground. Think of it like a complete diagnostic scan of Earth's fluid dynamics. So let's initialize the system and get right into it. Okay, let's look at the actual data here, because frankly, this sets the stakes for our entire journey. When we think of fresh water, we almost always picture the rivers and lakes right in front of us. But in reality, surface water makes up barely over 1% of the available fresh water on the planet. I mean, that's wild, right? The vast majority, nearly 69%, is locked away in ice caps and glaciers like a frozen desert, and an astonishing 30% is hidden right beneath our feet as groundwater. So the big takeaway here is that the water we see every single day is just a tiny, tiny fraction of the global system. Here are system scan parameters for this explainer. We'll start with the hydrologic cycle, move into basins and surface dynamics, and then look at sculpting fluvial landforms. From there, we'll sink below ground to check out groundwater systems and the costs of over-extraction before finally wrapping up with karst topography. All right, Section 1, the hydrologic cycle. Let's see how this whole thing builds from the top down, starting with the massive atmospheric engine that drives it all. So, water is in continuous circulation, and it's powered entirely by solar energy. It all starts with evapotranspiration. That's a combination of the sun vaporizing liquid water and plants actively contributing water vapor through a process called transpiration. That invisible vapor rises, cools, and then condenses around microscopic dust particles to form clouds. Eventually, those droplets collide and fall as precipitation. But here's why this really matters. Once it hits the ground, it either flows over the land as runoff, or it infiltrates the soil to recharge our groundwater. These surface and underground systems aren't just isolated silos. They are inextricably linked in this massive cyclical engine. Moving to Section 2, basins and surface dynamics. Zooming down from the clouds, we hit the Earth's surface. Let's see how all that precipitation actually organizes itself. Think of a drainage basin or a watershed like a giant funnel bordered by topographic high points called divides. And within that basin, hydrologists track what's called a water budget. It actually functions exactly like your personal financial ledger. On the income side, we have precipitation and groundwater inflow. On the expense side, we've got evaporation, human withdrawal, and outflow to the ocean. If expenses outweigh income, well, we start depleting our savings, meaning the stored water in lakes and aquifers. A super fascinating exception here is endorheic basins, like the Great Basin that covers much of Nevada and Utah. They are closed loops. There is zero outflow to the ocean. So in those basins, evaporation is the massive primary expense, and it just leaves behind these completely dry playas and salt flats. So how exactly does the water move through these basins? Let's decode the operating equation. Q equals V times A. Q is the stream's discharge. That's the total volume of water flowing past a point over a given time. V is velocity, and A is the cross-sectional area of the channel. As smaller streams merge together downstream, the discharge, Q, actually increases. But velocity is a bit trickier. It isn't uniform at all. The fastest water is found on the outside bend of a meandering river, or right in the very center, a zone called the Thalweg, simply because it's furthest away from the friction of the riverbed and the banks. It is literally fluid dynamics in its purest mathematical form. Section 3, sculpting fluvial landforms. Now that we understand how the water flows, let's explore the crazy stuff it does to the surface of the planet. Flowing water is without a doubt one of the most aggressive erosive mechanics on Earth. As a stream travels from its steep zone of sediment production down to its zone of deposition, it carries a heavy payload in three totally distinct ways. First up is the bedload. These are the heavy hitters, the large particles bouncing along the bottom through saltation or just drogging and rolling via traction. Next, you have the suspended load. Those are the smaller sand and silt particles caught up in the current that give rivers that classic muddy look. Finally, there's the dissolved load. These are invisible chemical ions, things like calcium and bicarbonate, that just hitch a ride. They're completely unaffected by how fast the water is moving. Ultimately, when a river hits a flat floodplain, it doesn't just flow straight, it meanders. Remember that high velocity on the outside bend we just talked about? Well, that fast water aggressively erodes the outer edge to create a cut bank, while the slower water deposits sediment on the inside bend, forming a point bar. Over time, these meander loops get more and more extreme. Eventually, the curve gets so tight that the river just takes a shortcut right across the narrow neck. The old, curved channel is totally abandoned, leaving behind this isolated crescent-shaped body of water called an oxbow lake. The river is literally dynamically altering its own path. Eventually, every river reaches a point where it slows down and has to drop its remaining payload. But the landform it creates depends entirely on the environment it's dumping into. Take alluvial fans, for example. These form in dry, arid climates. When a steep mountain stream suddenly bursts into a flat, open valley, it rapidly drops coarse gravel and sand in this massive fan or cone shape. On the flip side, we have deltas. These happen when a river enters a quiet body of water, like a lake or ocean, gently depositing fine silts and clays. And the shape of a delta tells a huge story. The Mississippi River, which is tightly constrained by human-engineered levees, pushes out this long, river-dominated birdfoot delta. Meanwhile, the wave-dominated Nile forms that smooth, classic triangular shape.
Section 4. Groundwater and Aquifer Systems. Okay, let's leave the surface behind completely and sink beneath the soil.
We're now looking at the subterranean reservoirs that hold 30% of our fresh water, aquifers. But here's the thing, a rock can't just be any rock to be a functional aquifer. It absolutely needs two critical properties. First is porosity. That's the percentage of empty pore space between the rock grains. This dictates the aquifer's ability to act like a sponge and actually hold water. But porosity alone isn't enough. You also have to have permeability, sometimes called hydraulic conductivity. That's the connectivity of those pore spaces, because if the pores aren't connected, the water is just trapped. So a functional aquifer needs both high porosity to store the water and high permeability to allow it to flow out into a well.
But not all aquifers are created equal. An unconfined aquifer is entirely open to the surface. Water simply infiltrates down from rain or streams, and the top of this saturated zone is what we call the water table. A confined aquifer, though, totally different beast. It is sandwiched tightly between impermeable layers of rock or clay called aquitards. And because the water often recharges at a much higher elevation far away, this trapped system gets highly pressurized. If you drill a well and breach that pressurized zone, the water is forcefully pushed upward by what's called the potentiometric surface. That creates a flowing artesian well. Yep, zero pumping required.
This invisible subterranean flow isn't just magic. It can actually be translated into pure mathematics. Way back in 1856, a French engineer gave us Darcy's law. It essentially states that groundwater discharge, our old friend Q, is driven by the rock's hydraulic conductivity, K, multiplied by the cross-sectional area, A, and the hydraulic gradient. That gradient is just the change in pressure over distance. To put that in everyday terms, groundwater flow is dictated by how easily the water can move through the rock and the pressure difference that's pushing it along. It's literally the hidden mathematical pulse right beneath our feet. Section 5. The costs of overextraction. What happens when we start messing with that delicate underground math? Let's check the system warnings. When we pump water out of a well faster than precipitation can naturally recharge it, we aggressively alter the system. Pumping creates a localized downward dip in the water table around the well bore. We call this a cone of depression. Now, if you only have one small well, the cone might be pretty minor, but when you have multiple high-capacity wells and those cones of depression actually start to intersect, the drawdown massively intensifies. Going back to our earlier legend analogy, this behaves exactly like a massive overdraft on our water bank account. We are rapidly burning through the savings. In the real-world, consequences of this groundwater mining are incredibly severe. When we continually overdraft this system, natural discharge areas like springs and streams just dry up completely. But even more alarming is the loss of pore pressure. See, in many aquifers, the water itself is actually helping to hold up the skeletal structure of the sediment. When you drain that water out, the clay layers compress. This causes irreversible land subsidence. Basically, the ground literally sinks. We are seeing measurable subsidence and massive earth fissures right now in heavily pumped agricultural regions, like Utah's Cedar Valley and California's Central Valley. The land is effectively collapsing in on itself. Section 6. Karst topography and caves. For our final scan, let's look at a completely different, almost alien way that water alters the underground landscape. The crucial point here is that water doesn't just mechanically push rock around, it can chemically dissolve it. As rain falls through the atmosphere, it picks up carbon dioxide, which creates a weak carbonic acid. When this slightly acidic rain seeps into solid limestone, which is mostly calcium carbonate, a chemical reaction kicks off.
The acid slowly, steadily eats away at the solid rock over thousands of years, carrying it away as dissolved chemical ions. This silent, invisible chemical weathering creates some of the most radical, unpredictable subsurface terrain on Earth.
This dissolved limestone terrain is called karst topography, and it leads to some truly bizarre and sometimes dangerous landforms. Because the rock is literally being hollowed out from below, you get sinkholes, sudden, catastrophic collapses of the surface right into underground caverns. It's a notoriously common issue in residential Florida, for example. You'll also see disappearing streams, where surface water just vanishes into a subterranean void. But it's not all destruction. When that mineral-rich water drips into empty cave systems and evaporates, it redeposits the calcite. That forms spectacular speleothemes. You know, the beautiful stalagmites rising from the floor and the stalactites hanging from the ceiling.
And that brings us to the end of our planetary scan. We've explored how water moves, how it violently carves the surface, and how it quietly dissolves the bedrock below. But I want to leave you with a provocative thought to ponder. We saw earlier that surface water is just a tiny fraction of our supply, meaning we rely heavily on the invisible groundwater beneath us. So if that groundwater takes hundreds or even thousands of years to naturally recharge, what exactly happens to our civilization's fragile water budget when we relentlessly mine these ancient aquifers like they're just a finite ore body? It is a critical system warning that we absolutely cannot afford to ignore. Thank you so much for joining me on this explainer, and keep questioning the incredible systems operating all around and beneath.